Okay, we've finished with classes and with associations. Now let's talk about association classes. Association classes are pretty straightforward. We're not going to generate new relations for them. We're just going to add attributes to relations that we're generating anyway. So let me use our usual example with the students in colleges, and we'll add some information to their application. Okay, so here's our UML diagram. We still have students applying to colleges, and then we've added a association class, which, as you remember, is attached to an association, and it gives extra attributes for that association. So here we're saying when a student applies to a college, we'll have a date of that application and a decision of that application. The first schema that I've shown down here is what we would get if we use the techniques we've already learned without the association class. So the student class generates the student relation, college generates college, and then the applied association generates a relation that has a key from each side. And by the way, right now, let's say that there's no multiplicities or other information that's going to give us special keys. So in that case, the applied relation doesn't have any keys other than the two attributes together. And furthermore, because we have no special multiplicities, we won't be folding that relation into others, as we showed in the previous example. So now what do we do with our association class? Well, as you can probably guess, it's quite simple. All we do is extend our applied relation to include the attributes in the association class. So we just add date and decision right here, and then we're all set. Now there's actually a few things I want to mention at this point. First of all, I discussed in the video on UML modeling the fact that UML assumes when you have a relationship or an association between two classes, there's at most one instance of that association between any two elements of the class. And that is can be seen quite well in this relational schema, because we're assuming we have at most one relationship between any student and any college, and then we have associated with that one relationship the date and decision. A second thing I wanted to talk about at this point in time is the fact that we, for an automatic translation, require that we have a key for every regular class. When I mentioned that at the beginning of the video, I wasn't able to motivate it very well, but this example explains things pretty well. When we want automatic translation, the translation for an association requires a key from each side, and each side is going to be a regular class in that case. So we needed to have a student ID or some key for the student class, and we needed a key for the college class in order to capture the association. On the other hand, here the application info is not a regular class. This is an association class, so we're just defining that as not regular. And we don't need to have a key for this one because we're just adding their attributes to the relation for the association itself. And the last thing that I wanted to mention is that the rules we saw for determining keys for the relations associated with associations and for folding in the relations for associations also work when we have an association class. And it just goes naturally. You just bring the attributes with the association class along with the attributes that you have for the association. You might want to give that a try on an example just to see how it works. But again, it's pretty straightforward. Now let's take a look at how self-associations are translated to relations. It actually follows exactly the same rules, but it's worthwhile looking at to see exactly what happens. So here was our first example of association, which was sibling relationships between students. So in this case, we generate the relation for the class, as usual, student ID, name, and GPA. And then we generate a relation for our association, just following the same rule we already had when we had an association between two different classes. So we need to grab one key from each side. Well, it's the same side that we're grabbing from. So the one thing we need to do is just change the attribute name so that we have two instances of the key attribute from the class, but they have different names. So you can see what we're doing here. We're just saying that we have a sibling relationship. We take the student ID from the two students who are siblings, and that pair becomes a tuple in our sibling relation. And because we have stars on both sides, so we're not making any assumptions about multiplicities, we don't have any 0.1s or 1.1s, then we don't have any key for the sibling relation except the two attributes together. Now, the other example we had in a self-association was colleges being branches of other colleges. So here's our college relation that we generate with the usual attributes. And then we have our, that's the key there, we have our association, which we're calling branch, which takes a home campus and a satellite campus. And since we've labeled those two sides, we can actually use those labels as the attributes for the relation we generate. So we'll call it branch, and we'll have home and satellite. So that's saying that the satellite, the campus on the college on the right-hand side, is a satellite of the one on the left-hand side. Now, these values here will be college names. That will be the domain that we're drawing from, but we're calling them home and satellite to distinguish their roles in the association. Now, what about keys? We said before that every campus, every satellite campus has exactly one home campus, so we write it that way, and that a home campus could have, I think we said something like 0 to 10 satellite campuses. But in terms of generating our relations, the only really important thing is this one-to-one, and if you remember what our rule said, it said that if we have one-to-one on one side, then the other side is a key in the association relation. So what that would tell us is that satellite is a key here, and that does make sense. So we'll only have each satellite's home campus listed once, but home might have many satellites, so the left-hand side would not be a key. Okay, we're getting there. We finished the first three, and now it's time for subclasses. This is a pretty big one. First of all, it turns out that there's, well, at least three, and three commonly used translations from a subclass relationship into relations. So let me set up a generic subclassing setup, and then we'll talk about the three different translations and when we might use which one. So here's our generic setup. I had to draw it a little funny to fit it in the space. S is our superclass, and then we have two subclasses, S1 and S2. And just as a reminder, what this says is that we have objects of type S, and they have a key attribute called K and another attribute called A, and then we have subclasses of those, one called S1, which will have attributes K and A, and will also have an attribute B, and a different subclass, S2, that will have attributes K and A inherited from its parent, and then an additional attribute C. Now, there are three different ways, as I said, at least three, that we could translate this UML diagram to relations. In the first way, we have a relation for each of our classes, including the subclasses, and the subclass relations will contain their own attributes plus the key of the superclass. In the second case, we still have one relation for each of our three classes, but in this case, the subclass relation contains all of the attributes from the superclass. And in the third case, we just use one mega relation for the whole thing that contains all of the superclass and subclass attributes. So let's take a look at what the three different translations would produce for this particular setup. For the first one, we'll have our relation for S that's going to have K and A. Then we'll have one relation for each of the two subclasses, S1, that will contain the key for the superclass, so it'll be K, and that will still be a key here for the subclass, and B. So to find all components of an object of S1, we'll get its A component from the superclass following that key, and then we'll get the B component from this relation. And then finally, say S2 will be similar. It will have the key for the superclass and attribute C. Again, what this will require is some assembly to get all attributes of the subclasses. Now let's look at the second translation. We still have the superclass, and our subclasses now are going to contain all of the attributes that are relevant. So they'll have the key attribute from the superclass. They'll also have attribute A and attribute B. And then S2 will similarly have K, and then A, and then C. So in this case, what we can see is that when we have an object that's in a subclass, all of its information will be in its subclass relation, and the superclass will only be used for objects that are in the superclass but not in any of the subclasses. And the third translation says, let's just make a mega relation that contains everything. So it'll have the key attribute K and A and B and C. And in that case, we can see that we may have some null values. So if we have an object that's only in subclass S1, for example, it would then have a null for attribute C. If we had an object that was only in the superclass and not in any of the subclasses, it would have a null for both B and C. Now, as you may have noticed, what has already been on the slide the entire time is that the best translation may depend on the properties of the subclass relationship. And if you remember, we had the properties overlapping versus disjoint and complete versus incomplete. So overlapping meant that we might have objects that were in more than one subclass. Disjoint meant that's not possible. Complete said that every object that's in the superclass is also in at least one of the subclasses, where incomplete meant that said that there would be some objects, or they could be, that are in the superclass and not in any subclasses. Sort of alluded to how some of those properties affect the different translations, but let's look at it very specifically. Let's suppose, for example, that we had a heavily overlapping subclass relationship. In other words, we have many objects that are in multiple subclasses. If that's the case, then we might prefer design 3, because design 3 captures all of the different attributes in one place. So if many objects have all those attributes, we might like to just have them together rather than needing to assemble them from the different pieces. On the other hand, let's say that we have a disjoint, and furthermore, let's say it's complete. So we have every element being in exactly one subclass, and there are no elements that are in just the superclass. So in that case, we might like to use design 2, because design 2 puts each object in its individual subclass relation. And furthermore, since it's complete, we could actually, in this particular case, get rid of the first relation. We wouldn't need that. And so the best design would be number 2, modified to only have the subclass relations. So now let's revisit our gigantic example from the UML modeling video and see how that would be translated to relations. So just to remind you what's going on in this big diagram, we have students, and students have a student ID and a name, and then some of our students might be foreign students and they have a country. Some of our students may be domestic students and that they would have a state and a social security number. And we'll assume that every student is either foreign or domestic. And then some of our students are AP students, and interestingly they have no attributes, but those are the ones who have an association called TOOK with AP courses. AP courses have a course number and a title, and then when a student takes an AP course, there's an association class that says the year they took it and the grade they got. So let's translate this to relations, the whole diagram. And we're going to use the first translation from our 3 schemes. So that's the one where the subclass relations contain the superclass keys and then all the specialized attributes. So let's start by generating the relation for the student class, and that's straightforward. That's just the student ID and the student name, with the student ID being the key. And then we're going to generate one relation for each of our 3 subclasses. So that would be the foreign students, which will take the key then from the student relation, so their student ID and the country that they're from. There'll be the domestic students, and there we'll have again the student ID inherited from the superclass, and the state they're from, and their social security number. And then we'll also have the AP students, and those have none of their own attributes, but we can get the key, and we do, from the superclass. So this is just going to be a list of the student IDs who are AP students. Now let's keep going. So let's take a look at AP students taking courses. So we'll have from the AP course class a straightforward translation to the course number and the title of the course. And then finally we're going to have a relation for the fact that an AP student took classes. We had some multiplicities on that the first time, but neither of them were 0, 1 or 1, 1, so they're not going to be relevant in changing our design. So took is going to have the key from both sides. Well, we don't see any key in here, do we? But subclasses always inherit the key from their parents. So the key here is implicitly the student ID, and that's what we'll be using here, student ID, the key from the right-hand side, the course number that they've taken, and then we'll have the 2 attributes from the association class, the year and the grade. So this actually looks like a pretty good design. Let me just make a few comments. The first one has to do with the AP student relation. So if every AP student does take at least one course, so if we have, for example, a 1 ... something over there, then we could actually eliminate this relation, because every student ID that appears in AP student will also appear in the TOOK relation. So this one will be redundant in that case. So again, that could be eliminated based on the multiplicity, though I wouldn't really expect an automatic translator to necessarily figure that one out. Another possibility I should mention is that we could have a primary key specified here for domestic students for Social Security numbers, since we would expect that to be unique, and that would translate to a key here. But let me be clear, this would be a separate key. It wouldn't be Social Security number and student ID together, but these would be two different keys. And in SQL you can actually distinguish between those two, but we can't do it the way we've written the relations here. And finally, let me mention again that requirement that we have keys for regular classes if we want to do translation automatically. And you might have noticed that, for example, we certainly didn't have a key here for foreign student, with country being the only attribute. But subclasses are also not considered regular classes. So subclasses and association classes don't need to have keys, and we can still have an automatic translation. Logically, subclasses are inheriting their keys from their superclass, and that one does need to have a key in order to have automatic translation.